Welcome all to this 15th lecture of Principles of Statistics. In the last lecture, we started with decision theory, which, as I said, is a unifying theory for all types of inferential procedures. And we spoke about Bayes' risk and Bayes' rules. And today we're going to take a more frequentist approach and introduce the concept of minimax risk. And we'll also talk about admissibility. And these two concepts, together with the Bayes' risk, we're going to, at the end of the lecture, put them together into some result. Yeah? Okay, so let me then start with minimax theory, or minimax risk is the part of the theory that we are interested in. So this is the second bit, and this is minimax risk. And so before going into it, let me just define a concept that is more from the Bayesian world, but that is going to make sense within the context of minimax risk. Okay, so definition. This is definition 3. Okay, that's terrible. So definition 3. So a prior. Okay, so let's talk about. Okay, so a prior pi, we say that is called or is said to be least favorable okay if we have that it's risk for the, so let me define this in a sec. So I don't think I used this notation of delta subscript pi, but maybe I did. But anyway, I'll just define it in a sec. So if, okay, so the condition is that it's risk when, this delta pi is the actually, so this, let me just say, of course, this has to be for all pi prime, yes. Okay, so let me maybe say here for all pi prime. Okay, so where this delta pi is the pi Bayes rule. Yeah? And this, of course, applies to the pi prime as well. Yeah? Okay, so rule. Okay, so what we have here is essentially, so this is something like, I guess if we were talking about the risk, so if we were talking about this guy here, then what we have here is the, so r pi delta pi is the worst case Bayesian risk. Right? So you'll be thinking, okay, so why is he introducing the worst case Bayesian risk when actually you would like to have the minimum, the minimal Bayesian risk? Well, it will make sense in a second now that we're going to introduce the minimax risk. Okay, so just bear with me for some time, just a bit. Okay, so definition 4. So let me define the worst case risk and not, Bayesian worst case risk. So first, and it is also called the maximal or worst case risk of a decision rule. I remind you that I'm going to use this DEC as short for decision. So rule delta is the following quantity, so we write it as, we denote it by this. So this depends on the parameter space, and this is given, by definition, it's going to be the sup over the parameter space of the risk of the decision rule, right? So of course, when we're talking about these risks, we always have some loss function in mind, that is fixed. But we will, so I will essentially omit this throughout. Okay, so this is the worst case risk, and then with the worst case risk, we can define also, so the minimax risk, okay, and this is of a decision problem now, and this is important, but I'll be silently. So let me comment on this in a second. So let me define it first. So the minimax risk is simply the infimum of a delta of this Rm delta, okay, which is just by definition the infimum of a delta of the sup over theta of the risk, right? Yeah. Okay, so let me pause here for a sec, because the definition hasn't finished. But, what I want to say about this is that this infimum is not over all of the possible decision rules out there, right? So it's just over all of the decision rules for the decision problem at hand, right? So first of all, we fix a decision problem with, with some parameter space, and then we need to choose the loss that we're going to use for the risk, but this is sort of like equivalent to this capital R, right? So to this risk function, and then we find, this inf sup, which is what is giving the name to minimax. Okay, so this is min max, right? This is again really bad writing. Okay, but we will be, from now on, we'll be avoiding mentioning that we have a fixed decision problem, fixed parameter space and a fixed loss function. So these things are sort of assumed, as we're talking about these things. Okay, so this is the first thing to say. The second thing to say about this definition is, why would we be interested in this inf sup quantity? So let me, before mentioning the reason, let me finish the definition. So a decision rule delta, again, I will write this just for the last time. So in a decision problem, in a given decision problem, is called minimax. Well, it's clear what's coming, right? So it's minimax if there exists an R, okay, or really a loss function such that the worst case risk of this delta equals the minimax risk. Okay, of the problem. Okay, so, oh, I'm sorry. Okay, so let's comment a bit on this. So first of all, maybe let's say why we're interested in this supremum over the parameter space. So I think this should be already sort of clear to some of you, because I've been mentioning that, you know, from a frequentist point of view, well, or even just in general, I mean, you don't know the parameter, right, when you're doing statistics. So, well, okay, so that's a bit frequentist because I'm already saying the parameter. So, yeah, so you don't know this parameter, and so therefore you want your procedures to be uniform across this parameter space, right? And so this soup here, what it is saying, even though it is called the worst case risk, I mean, what you're saying is, well, I don't know, I really don't know, you know, the parameters, so therefore I should be in the worst case scenario, right? And that should still work. You know, my procedures should still work for the worst case scenario. And, you know, that should be what defines the difficulty of my problem, is this worst case scenario. But then, you know, what I can say is that we're really smart, and what we are going to look for is the best decision rule for this worst case scenario. Yeah. So that's what we want to be ready for. So we want to be ready to minimize this maximum, yeah, or this worst case scenario. We want to find the best estimator for it. And this also, you know, sort of in itself defines the difficulty of the problem. So this whole minimax risk, yeah. And so we'll be sort of looking for minimax decision rules, and that's from a frequentist point of view, right? Because a Bayesian may disagree with this and say, well, why would I be in the absolute worst case, you know, or consider the absolute worst case world? Sorry, excuse me. Yes, okay. And instead, why don't I just weight up, you know, the parameter space through my likelihood, through my prior, right? So this is basically what this base risk is doing, and this least favorable prior is going to be sort of related to this minimax risk concept. Yeah, so the two concepts are going to be so. So let me just write this down in words. What I was just saying. This discussion. So remark. So the minimax risk is criticized by some as being too conservative, right? And I must say that this is really a small community that would criticize, well, maybe not. It's certainly a majority of statisticians would be happy with the minimax theory. Okay, let's put it this way. But from a frequentist point of view, it is a very reasonable concept, right? Okay. And let me just make, you know, a comment that will relate to the base risk. So as a worst case risk, and this is of course in the parameter, it cannot be lower than any average risk, right? This is, of course, average over the parameter space, or the parameter risk. So any average risk, by the way, should be, so this is some base risk, right, for some prior. Okay, so in maths, what I'm saying is no more than, r pi of delta for some delta. So this, by definition, is this integral over the parameter space of the risk. And then we integrate this with respect to the pi. And of course, this is going to be bounded, upper bounded. Maybe let's go to the next line. So this is upper bounded by the sup over the theta of this r delta theta. And then you get the integral over the parameter space of the prior. And then, of course, this is going to be just the rm at delta with capital theta and a 1 coming from the integral, right? So this is saying that, this is less or equal than that. And of course, the left-hand side, so the quantity here is lower bounded by the base risk. So it would be just the risk when you plug in the base rule. And so really what we get is actually that, the least favorable prior, even the risk for it, which is, like a worst case Bayesian risk, will be lower bounded by this sort of more frequentist base risk, worst case risk. Yeah. Okay. And so we see that there is, a clear relationship between the two concepts. And the question then is, can we say more about this close relationship? Or maybe, when do the two coincide? Well, you want some sort of equality rather than inequality, right? So let's just introduce, let me just mention that. So minimax so since r pi delta is always greater than or equal to this, minimax and least favorable risk can be or are related. Yeah? Okay, so let's give an instance of this relationship that one can have. So proposition 2, suppose that pi is a prior on this parameter space such that we have that the base risk is equal to the worst case risk. Okay. So then we can say several things. First, and this is of course pi. Yes. Sorry. So first, pi is least favorable, okay. Then second, delta pi is minimax, and 3, if this delta pi is unique as a pi base rule, then we have that it is also unique minimax. Yeah? Okay. So these statements should be sort of not too hard to prove, given this sort of inequality that we were using. So we're going to use these ideas again and again, yeah, to prove this. Okay, so prove. Okay, so the first bit is just pretty much what I was mentioning in words. So let pi prime be any other prior, then we have that, if we look at the base risk of this guy, this is going to be, I guess, okay, so let me write it out. So this is over the parameter space, the risk for delta pi prime theta, pi prime theta, d theta, and this is, of course, upper bounded by the same quantity when we plug in the delta pi, from the statement, because we know the delta pi prime minimizes the risk for the pi prime prior. And then now what we know is that, we can do the same calculation as before and take the sup out from the integral. So we get this Rm of delta pi, and then a capital theta, and then we get the integral of the pi prime, so that's 1, just as before, and this by assumption, okay, so this is our assumption, we have that this is exactly the R pi delta pi, okay, and then this means that the pi is least favorable, right? Okay. All right, so that proves the first part. Then the second part, again, is the same sort of, same ideas are used. So let delta be any other, or any decision rule. Okay, then what can we say? We can say that, so let's look at the worst case or the maximal risk for this delta. So this guy is going to be lower bounded, so by the same calculation that we did here. Okay, so this is just the R pi delta. Okay, and then this is of course lower bounded by this, right? Because, yeah, for obvious reasons. And then by assumption, this is now Rm delta pi here. And so, you can take now the infimum and have that, and have the conclusion here. Okay, so, and the conclusion follows by taking the infimum over this delta, right? Okay, and then the last bit actually follows from this that we have here, so from this chain of inequalities. So if delta prime is unique, pi base, then what happens? Well, we have that this guy here is strict. Okay, and so if it is strict, then we have that once you take the infimum, you also get a strict inequality, and so then we have a strictly, we have a unique minimax decision rule, right? Okay, so that wasn't hard, but it's actually, it's an interesting set of conclusions, yeah. So let me maybe now summarize the proposition in words. So let's see. So in words, so we have some sort of discussion. So in words, what we've seen in this proposition is that if the maximal risk of a base rule for a given prior equals the so this would be just the base risk, right? Then we have that the prior is least favorable, and also that its base rule is minimax. Okay, so what does this mean? Well, it means that we have essentially a recipe. Yeah? This is a recipe to find minimax rules, right? Okay, but it is important to also emphasize that there can be minimax rules that are not, they're not satisfying this relationship, or this equality. But not all minimax rules are of this type, if you like. Okay, so let me just give you an example, even though we're not going to go into details of it. So later on, so later on, we show that if we have data coming from, so this experiment we've been talking about a lot already. So if we have IID data from a normal distribution with some mean and variance 1, then the MLE is this X bar, and this guy is actually minimax. Yeah? Okay, so this is minimax, and this is also true for more general model. Theta sigma squared, and for multivariate. And note that, of course, this MLE is unbiased, and we said that an unbiased estimator cannot be, at least for the quadratic risk, and this is essentially what is going on here. So I didn't mention this. Yeah, okay. So this is for the later on. We showed that it's minimax for quadratic risk. Yeah? Okay. Let me just write it here. So okay, so this is an example then of an unbiased estimator that will, cannot be Bayes, because we saw that for the quadratic risk for any prior, but it's still minimax. Yeah, so we certainly haven't gone through the route of it being Bayes, yeah, in any way. Okay. So let's now give a simpler recipe that we can get from the result that we just introduced, so the proposition. Okay, so corollary, or maybe let's mention this. So the following is a resulting simpler recipe. So this is corollary 1. Okay, so if we have a unique Bayes rule, so if a unique Bayes rule has constant risk, then it is unique minimax, right? And this is actually just nearly immediate. Okay. This is immediate. Okay. So see the example sheet. We have to show it, but again, this is just a well, okay. Actually, I'm not sure if this is in the. All right. Okay. Let's just show it now. So by assumption, right? So by assumption, what do we have? Well, we have that this R delta pi, right? Theta is constant, right? So this is therefore, okay, so this is constant, and if it is constant, then surely it equals its maximal risk, right? Right. Okay. So then what do we have? Well, we can write that this Bayes risk is going to be, okay, so just to write it out slowly, this is R delta pi theta, right? Pi theta d theta. Well, if this guy is equal to so if this guy is just, yeah, okay, I think it's clear, right? That this should be this. Okay, because you can take the sup out, just because in this case is actually, you can take out the R of the integral because it's a constant, and the remaining integral is 1, and this constant by this observation is equal to the maximal risk, right? This is simple, and then okay, maybe let's say then, and proposition 1 applies. Yeah? 1 or 2? Yeah, 2. Okay. Okay. So let me give you an example of in which this recipe works. So you will have to complete the details for the example sheet for one of the exercises. But, the model and setting is the following. So in a binomial and theta model, so you can consider a prior that is a beta a b prior, and let's call this pi a b, so dependence on these guys, and this is on theta 0, 1. So we consider this, and we also consider the quadratic risk again. Okay, so then, things work out basically in this example. That's the conclusion, but, just being a bit more formal, what we want to say is that the unique Bayes rule so the unique Bayes rule is this delta pi AB now, and this is of course now the posterior mean, okay, because of the result we had from the last lecture. So this is posterior mean, and you can find a pair of A and B star such that the risk of this, so for these guys, and this is a risk for all theta, so this is constant. And this is of course in theta. Okay. And note that in this case, this guy is not the MLE. I guess just as an observation, because before we gave an example of a model in which the MLE is minimax, and in this case, we construct this minimax rule, and it doesn't necessarily coincide with the MLE in this case. Yeah. Okay. So then the last concept I wanted to talk about is admissibility. Okay. So admissibility, well, this is a very natural concept, yeah, to consider. So definition 5. So we say that a decision rule delta is inadmissible rather than admissible if there exists another decision rule that dominates delta. And what does dominating mean? It means the following. So it means that delta, the risk. So the risk at delta prime is always not greater than that at delta, so for all theta, and there exists a theta prime such that you have a strict inequality, right? So then in this case, why would we prefer delta over delta prime? Well, there is no reason to prefer it, right? So that's why it's inadmissible. And so we say that delta is admissible if basically it is not dominated by any other decision rule, right? So if it is not dominated. And again, I'm silently fixing the decision problem. Yeah. So of course, this is all for the decision rules in the decision problem under consideration. Okay. So what can we now say to relate all of these concepts? So let's say proposition 3. Okay, so we have that a unique Bayes rule is always admissible. Yeah? So that's good news for unique Bayes rules, which, by the way, if you have this risk, for instance, constant risk or the other one that we're considering in proposition 2, then you get minimax as well, right? So now let's do slight converse, not really, but sort of related. So admissible, so if delta is admissible, and we have this condition of constant risk, then it is minimax. Okay. Okay. All right. So the proof is actually for you to do. So this certainly is, I think, now. So this is example sheet. Okay. And I will just make a last remark, which is, non-examinable. You don't need to know the details, but the way I'm going to remark it, really, there's no way I could examine on it. And that is that. So we've seen that a unique Bayes rule is admissible, but the question then is there any way? So that clearly gives a construction, right? But then maybe, as in a recipe to construct an admissible rule. But generally speaking, being a unique Bayes rule is not necessarily just the easiest. Yeah, okay. So the admissible, let me maybe say, in other words, the class of admissible rules is actually much larger than just those that correspond to unique Bayes rules. Okay. So let me say that. So any admissible rule is the limit of a sequence of Bayes rules in some sense, yeah, in an appropriate sense. Okay. Yeah, so this is a bit more like from topology, right? But anyway, I won't talk about that. Okay. Okay, so I hope you enjoyed this lecture, and I'll see you again in the next one, in which we're going to talk about, this sort of these concepts within the normal model. So we're going to, go back to this example that that I mentioned I would finish, or that I would actually write out. And with this, we're also going to talk about the James Stein estimator, okay, which is an important estimator that I think if you're attending statistical modeling, that you may have come across already. Okay, right. Thank you for your attention, and see you again on Friday.